Okay, welcome back everyone. We're moving on to chapter 12, which is titled Numerical Methods. This is going to be the chapter which basically encompasses the way that the real world, or at least industry, the industrial real world, the approach that they take to differential equations, because most, I should mention this, most differential equations which exist in the real world I don't know why I have two L's there, which exist in the real world, and put quotes under that too, so whatever you're going to consider the real world, cannot be solved in closed form. You know, this is anything from your Magnus expansion in the linear ODEs, but non-autonomous ODEs setting, to your just terribly nonlinear ODEs in either dimension greater than 2, greater than or equal to 2, so dimension greater than or equal to 2, or with some order greater than or equal to 2. And we know because of our theorem 4.4.1 that the order and the dimension greater than 2 kind of go hand in hand. But nonlinear ODEs with those properties really can't be solved in any sort of closed form, except for extremely specific situations. And so because of that, we can't solve them in closed form. We'd like to numerically approximate their solutions very, very well. And that's what this chapter is going to be all about. I've kind of pushed it to the end of this course for a couple of reasons. The first reason is that when you leave the course, this will actually be the most powerful tool in your toolbox. A lot of people will pay you a lot of money for knowing these tools. And secondly, there are certainly some things that were important that we've covered so far to really be able to understand this chapter perfectly, maybe the way that we should understand it. So let's start with what I'm calling local approximation via linearization. This is jumping back to chapter 10 when we first learned how to linearize some nonlinear ODEs. We're just going to cover in more detail. I know I went through one example in chapter 10, but we're going to cover in more detail what it would mean to approximate a solution to a nonlinear ODE locally, at least using linearization. And really, to get into numerical methods at all, I'm toying with putting this first section as like a section 0 here. We have to talk about these notations. These notations are called big O and little o notation. And so there I reference that it's pronounced as big O and little o. Some people will call this Bachmann-Landau or asymptotic notation. I almost never hear either of those two. I'll hear order notation as well. But often you'll hear big O or little o. And this is just a useful notation to describe the limiting behavior of two functions. So maybe I'll write this down. Useful comparison of growths or decays of one function to another. So the way that this notation works is that we say that f basically is related to g, two functions f and g. I'll say f is big O of g. Big O of g as t goes to t naught if the limit superior, which you can just think about this as the limit, and that will be perfectly fine for the meanings of this course, as long as the limit superior of f divided by g is a finite number. So all we need is that f over g is some finite number in the limit, and t naught could be possibly infinity. Maybe I should mention that here. Possibly infinite, right? I could talk about this limiting at infinity. And we use that as big O, and we say little o if in fact the limit has to tend to 0. So it's like little o is like the special case of big O, where little o is big O, where the quote-unquote finiteness at the limit is 0, right? Maybe this tends to some finite number m there. If that limit is actually 0, then we have little o. Okay, so this is fine to define it as such. And I do say so long as g of t is not equal to 0 in both cases, because I am dividing by g of t here. If it's only equal to 0 at like finitely many points, then just skip all of those points and you still get the same limiting behavior. But if you run into some problems with zeros, you have to play a little bit trickier game. But you can look on the Wikipedia page for that if you're worried about zeros. Let's look at a nice example of this. So square root t plus t squared. We call this order t as t goes to infinity. Why should we think about that as order t? Is like in our head, we're thinking about the square root coming down and hitting t, and we have like t to the 1/2. It comes down and hits t squared, and that's like t. And the more powerful of the two t's at infinity is the t to the first power, and so that's why it's order t. But the way we would truly prove that is we actually calculate the limit, right? If we're saying it's big O of t, we're going to calculate the limit as f is divided by g, which in this case is root t plus t squared is divided by t, and you go through your standard calc 1 and 2 limiting arguments there. And we end up with 1, which is certainly a finite number. If we increase the power of t in my order comparison, right here I'm comparing the function root t plus t squared to just t. If now I'm comparing root t plus t squared to the function t to the 1.1, then actually this is little o. Here we had big O because it was a finite number. Here we will end up with little o because if we compute our limit comparison, we truly end up at 0, right? If you just go through the limit comparison process, you'll end up at 0 there, which is what it means to be little o. And in those two cases, that's when t naught was infinite. I can talk about t naught being finite in the next example, and I can look at the same function on the left, but now it's big O of t to the 1/2 if my limit is headed in a different direction, right? So these comparisons only exist as the limits end up somewhere, and so if I change where the limit is ending up, now in this case I'm going to 0 from the right, then actually the root t plus t squared is order of t to the 1/2, right? And we can check that using our standard limiting arguments. We get a 1, which is certainly finite. And in fact, it's something like little o of t to some power less than 1/2 because we go through the limiting arguments and we end up with 0. And this is once again specifically as we're approaching 0 from the right. And so these are basically talking about limiting arguments, but it's kind of talking about what is the function behavior in that limit region, in the limiting region. So now why I'm including this in a numerical methods chapter, we'll often use these notations to describe how quote unquote good an approximation scheme is. And the reason why we'll say, relate this to like an approximation scheme is that if we're given maybe some function y tilde, and I'm using the tilde for very obvious reasons that, our word approximately, or our symbol approximately is basically made up of two tildes. And so I'm using the tilde over y to, in this entire chapter, be an approximation of some other function y. Then we call the order of the approximation at some point, maybe where it starts. It's the power n for which, if I take the ratio of my approximate to the original function divided by t minus t naught, that should look kind of like a difference quotient, even though it's not. We shouldn't think about it as a difference quotient. But if that ratio is order t minus t naught to the nth power, that's the order of an approximation. And of course, you could definitely write this as the following instead. I don't really like the above notation where we're dividing it by t minus t naught, but it makes more sense with saying it's order n if the right-hand side is just a power of n. If we go in traditional big O notation, this is saying that the approximating function is t minus t naught to the n plus 1 in big O notation there. And this is specific to a point, right? This is an approximation at a specific point. In this case, that point is t0, and that's why I'm really taking t minus t0 here. So if I'm approximating something at like 0, this just becomes t to the n for both sides there. And so that's why this notation is useful, because we're going to use it to classify how good of an approximation is. Let's just make a remark. The higher the n, the better the approximation. And this is because we're taking the big O notation at t naught, and a very, very high power monomial is going to look something like this. This would be like t minus 0 to the like 4th versus t minus 0 to the 1st. It's just like this, 0 to the 1st. And so the idea is that the higher the order, something like 4th, you stay near 0 for a lot longer time, at least between t0 and t1. And so for a lot longer time, your approximation is valid for a higher order. So there's a nice little remark that a 0th order approximation is always going to exist, right? As long as the function I want to approximate is differentiable, because actually if I just let the approximating function be the constant function, which is just the value at t0, then I can calculate this out, and I know that ratio goes to the derivative, which is finite, and so I'm necessarily already of order 0, because if I'm dividing this by that over there with an n equals 0, then that's order 0. So the local truncation error is not necessarily defined by big O notation, but it can kind of be related to big O notation. So we'll use the term local truncation error of some time step delta t, and that's just going to be the approximating function shifted by delta t. I'm looking at delta t times in the future from wherever I've started, and I'm subtracting the value of my true function at delta t times in the future. So, you can also say that if the approximation is nth order, you can kind of say that the local truncation error is O delta t to the n plus 1. That's a little bit tricky because it's only true for really, really tiny delta t. This should be its order delta t to the n plus 1 as like delta t tends to 0 from the right, or something like that. But we do say that about local truncation error, so that should just always be assumed to be what it means. So here's a nice example. We'll look at the approximation here for the IVP y prime equals negative y and y at 0 equals 1. I'm going to claim that the approximation 1 minus t is first ordered. Right, so 1 minus t is definitely not the solution here. We can get the solution really quick. Our solution is just y of t is e to the minus t by chapter 6 and or 7 methods. And if we calculate this limit, notice I've put a t squared in the denominator because I'm claiming it's first order approximation. So that number always has to be the order plus 1. And I expand with a Taylor series my solution, then this agrees with the Taylor series up to 2 terms, the constant and the linear term, and so then I start at n equals 2. And if I take the limit as t goes to 0 of the n equals 2 term divided by t squared, I just end up with 1/2, which is finite. And so there's a nice example of a first order approximation to the IVP. This next proposition is something I'm going to let you prove, but it's a very useful proposition. And that's that if a function is analytic at t0, the polynomial consisting of the first n plus 1 Taylor series expansion terms, which is the Taylor series, I should write this out. This is the Taylor series starting at k equals 0 and going up to n, so that's your n plus 1 expansion terms. That's always an nth order approximation. So that's something really useful to think of, but you'll prove that in an exercise. And then the next theorem is kind of the point of this section, and that's that if I have a non-linear Cauchy problem, or IVP, however you want to think about this, I've got some nonlinear operator n, possibly time non-autonomous, and I want to gain a nice local approximation, what I can do is I can linearize that, and under linearizing it, I'm not going through the work for you now, because you could do that from the methods from chapter 10 and do it, find that this is the solution. The solution to the linearized Cauchy problem is the following, where this is coming from the Magnus expansion. But ideally, make a remark, ideally, we don't need Magnus, right? There's ways around Magnus for a very large swath of these Cauchy problems once we linearize them. But possibly we might need Magnus. And so if we solve the linearized problem with Magnus, and this is what it looks like, right here, this is truly the linearization, or I guess the derivative of the nonlinear operator there, and you evaluate it at the initial condition. But the script d in both of the exponentials there, those are actually the Magnus matrices. And they're corresponding to the non-autonomous matrix, which is your derivative of the nonlinear operator. But that's going to be a second order approximation. Okay, so that's the primary result of this section, is that if I decide to solve the linearized problem, I gain a second order approximation. Now, recall that a first order approximation was just as good as a derivative. A 0th order approximation was just as good as a constant. So you have a derivative, or you have a constant, you have a derivative, which is basically the first Taylor series term. And then this is actually as good as a second order approximation. So you would feel like after linearizing, you're taking a derivative, so you'd think you only get a first order approximation because you've computed only one derivative, which feels like the first Taylor series version, but you actually gain a second order approximation, which is quite nice, because second order approximations are fairly good. We tend to like these approximations, but the work required to solve this linearized problem, perhaps with the Magnus expansion, is not necessarily going to be easy. There's the formula for you that will give you a second order approximation, and I have a proof as to why it's second order, because it turns out everything cancels up to the n equals 3 Taylor series terms. And it kind of comes from the fact that actually your first derivative is given right here. So as long as you have your constant term is given right here, your first derivative is given right here. And so actually the derivative of the nonlinear term is actually resulting from the second derivative in y, in the solution y. So as long as you agree there, that's why we get a second order approximation. Okay, so that's a nice long-winded proof. So here's an example of how we might use that. So we have, say, find a second order approximation via linearization to the following IVP. And we're going to rewrite the IVP in terms of the previous theorem so we can actually make it make sense. And let's just go ahead and calculate the linearization of the right-hand side here. So that's talking about this. Or let's calculate a derivative just so we get some practice. And recall, since this is just a vector field, so of a vector field, the derivative of a vector field is going to be your Jacobian. So we're really calculating a Jacobian matrix. So Jacobian matrix here will be partial y1 there, which gives me y2. Partial y2 there, which gives me y1 minus 2y2. Partial y1 here, which gives me y2 minus 2y1. Partial y2 here gives me y1. So this is d sub y of n, the Jacobian matrix. If I want to evaluate that at the initial conditions, maybe I'll use a new color here. Evaluating that at the initial condition 1, -1, if I'm calling this y0, maybe I want to evaluate that at y0. Then I get y2 is -1, so everywhere y2 shows up, I'm putting -1 in there. -1, -1, and here I have a 1 for y1. So I guess that gives me something like -1, 1 plus 2 is 3, -1 minus 2 is -3, and 1. And ideally, that's what I have below. Yes, so that's what I have below, just to show you where that matrix came from. Okay, so my linearization then looks like this of the right-hand side. And actually, I can plug the numbers 1, -1 in for y0 there, and execute the matrix across. And so I end up with a true linearization of the following, right? I have a matrix -1, 3, -3, 1, y plus 2, 2. That means my linearized Cauchy problem actually looks like the following. Right? So it doesn't look like what's at the top. That's the nonlinear Cauchy problem. The linear Cauchy problem looks like this. And we know exactly how to solve this because this is autonomous. It's non-homogeneous, but it's autonomous, so we know how to solve that. And solving that with our matrix exponential gives us the following, right? It's the following negative cosine root 2t and then some vectors there. But if we look at the approximation maybe to the actual solutions, what I have in black here is the real solution for y1, and gray is the real solution for y2, and red is the approximate solution for y1, and orange is the approximate solution for y2. So we can see near t equals 0, where we've initialized our linearization, we actually have really good agreement, or really good approximation for a good positive amount of time there. So that's really useful, and so that's a second order approximation. Okay, and that's actually all I have for you today. So I'll see you in class. Bye.